The next thing that I like to do is a little bit more ambitious. Now we have found the force on each electron. Now if you think about our original formula for the force on the whole piece of rod, you see that it is F equals to BIL. It has this value for current in the formula. But if you think about the electron, think about a single electron. As you can talk about the current of a single electron, of course, but if it's just a single particle, it is usually easier to think about the velocity of the particle. So, can I somehow have a formula where I can calculate the force on each electron using just the magnetic field and the velocity? It means a formula like this one where I just need to know the magnetic field and the velocity, and I can calculate the force on the electron. Wouldn't that be a lot easier than having to go through all this trouble to find the number of electrons? Indeed, there is a way, and in order to do that, we must first think about the velocity. Think about how we might find the velocity of each electron in this current. Now we might imagine that if the current is bigger, if we have a bigger current, then the electrons should also flow faster. And this suggests that there is some connection, that somehow the velocity of the electrons must be related to the current in some way. So what I like to do now is this. I want to try and calculate a value for the velocity of these free electrons. Let me clear this up. Oops. Right, the way to do it is to think about electrons flowing into this rod. Now, if I have electrons, say coming in from one end of the rod, let's say from this end of the rod, you can imagine that there are lots of electrons in the rod, of course, but there are also lots of electrons, say on one side of the rod, and waiting to come in. So there are lots of these electrons, and they will flow into the rod as the electrons that are already in the rod flows out of the rod. Okay, so there's always lots of flowing, lots of movement of the electrons. Okay, and the length of the rod is L. Okay. The L here. Let me put in those values again. The length of the rod is, I'm taking it to be 10 centimeters. The magnetic flux density, I take it as 0.1 Tesla. The current is 0.1 ampere, and I've calculated the force previously. Let's think about how to calculate the velocity of the current. Okay, well, at least the least I can do is to start by writing down the equation for the current. Charge over time is equal to the current. Right. So the charge over time is equal to the current, and so what I need to do is to find out how much time it takes for electrons to flow in and fill up the whole rod. As I said, there are already electrons in the rod, and as these flow out, new electrons will come in from the other end to fill the rod, and it's continuous, of course. But if I want to know, but I can still think about that there are a certain number of electrons in the rod, okay, which actually I've calculated in the last video. It was one of the numbers that I've just cleared away. Let me write down that number again. The total number of electrons in the rod, total number of free electrons is N is equal to 8.49 times 10 to the power of 21, and this was the number that I calculated in the last video. Okay, so I want to find out how long it takes. I want to find out how long it takes for this number of electrons to come in and fill up this rod. Okay, because if I know that, if I know the time that the electrons come in and fill up this rod, then I can find the velocity. Because when the electrons come and fill up this rod from, say, from this end, from just outside this end of the rod, it must mean that those electrons would have traveled this distance of 0.1 meter. And if I know the distance and time, I can find the velocity. But how can I find the time? Okay, this is how. There's a way to do it. You see, we know the current is 0.1 ampere. The time is what we need to find. Okay, let me write down what I have. We know the current. We know that this is 0.1 ampere. The time is what I need to find. Now I can find it if I know the charge. If I know the charge. Do I know the charge? Okay. I know the number of electrons. I'm talking about the charge of all these electrons that you need to fill up the rod. Okay. Now I know the number of electrons, the number of free electrons that fills this rod. That would be N. And we also know the charge of each electron, which is E. If you remember, E is 1.6 times 10 to the power of minus 19 coulomb. So this means that we know the charge. We can find the charge quite easily once we know this number. Therefore, we can find the time. And once we find the time, we also know the distance traveled is just the distance to move through this rod. Then we can find the velocity. Okay, so we have a plan now. So let's try this out. Okay, let me just rearrange this a little bit. I'm just going to write this out in terms of the N and the E. So N E over T. And now I want to find the time. Time is equal to, right, if I cross multiply, I get N E over time. And I know all this, N E over I. And I know N E and I. The N is this number here. 8.49 times 10 to the power of 21. We know E, that's that number there. 1.6 times 10 to the power of minus 19. And we know the current, that's 0.1 ampere. So we can use a calculator to find this. Okay, and the answer I got was 1.3 13590 of a second. But that looks like a very long time, and indeed, if I convert this to hours, it should be 3.8 hours. Should be 3.8 hours, and that seems like a long time that it takes for the free electrons to fill up this rod. Okay, but we must not forget that there are lots and lots of electrons. Okay, and that the total amount of charge here is a very big number. It's this value here. Okay, so that's why even in a short time, in the short time of 1 second, there is enough charge that comes through to give you this 0.1 coulomb per second of current. So having now found the time, now, we can find the velocity. The velocity is just the distance traveled divided by the time. Right? L, the 0.1 meter, is the distance that the electrons need to travel as it comes in to fill the rod. Right? Like this, for example, in case this seems difficult to understand, we can imagine that an electron that starts near this end of the rod, maybe an electron here, it would in this time travel to here, okay, over this distance, and the electron that would arrive, maybe that would just arrive here, just coming to this end of the rod during this after this time, this electron, let me use a different color for that, this electron that has just arrived after this time would have started from further back at a distance of, it should have started further back at a distance of 0.1 meter. Okay, so as this electron just outside this end of the rod moves by 0.1 meter, so an electron which is 0.1 meter away would have just arrived this end of the rod. And in between, of course, if I have an electron in the middle, alright, after this time, that electron will move 0.1 meter to the middle of the rod. Okay, so that's the idea. So therefore, I now have all the information that I need. L is the 0.1 meter, and T is this time, 13590. And using my calculator, I would find 7.36 times 10 to the minus 6 of a second. Now that looks like a really small number. It's just about 7 microseconds. 7 microseconds. So it looks as if the electrons are crawling, right? They're literally crawling into the wire really, really slowly. Okay. Now, as I've mentioned, we can kind of understand why this number is correct, because there is a huge number of electrons there. So even though the electrons move really slowly, after 1 second, there will still be enough charge to enter to give you the 0.1 coulomb per second of current. But what I would like to mention here is that this number, although it's the correct answer for this example, it is not the actual velocity of each electron. This number here is an averaged velocity. This is an average value. Now, each electron, if we imagine that we can actually see the electrons moving. Now, the electrons are actually moving in all sorts of random directions. They're moving in random directions, completely random. Right here, there, up, down, left, right. In fact, we can actually think of the electrons, the particles of electrons in a metal, these free electrons, as if they are molecules in a gas. Right? The same gas that I described when I talked about ideal gas in a much earlier in the earlier videos. So in a gas, you would imagine that the molecules, say of oxygen and nitrogen in the air, would be moving randomly and would be moving at very high speed. And in fact, that is the same for the electrons here. We can use the same picture for a gas. We can apply that same picture of a gas to the electrons. The electrons would look just like a gas in many ways. But then you might ask, if the electrons are moving in all sorts of random directions, then, and in fact, they would be moving at very high speed. Right? Typically, the speed might be as much as maybe 10 to the power of 6, like 1,000,000 meters per second. Right? The complete opposite of 10 to the minus 6. So if it is moving, let me just correct this. This should be meters per second. So if the electrons are moving so fast and in so many different directions, what do we mean by this small number here? So as I explained, it means an averaged value. Now, without the current, if there's no current, if the current is 0, the electrons would be moving in all sorts of random directions, and the average velocity would be 0, because, for example, there would be roughly the same number of electrons in one direction as number of electrons in the opposite direction. But when there's a current flowing this way, we would have slightly more electrons going in this direction than there are electrons going in the opposite direction. So as a result, we have an average velocity with a small average velocity which is moving in one direction.